Today, correlation and simple regression. I don't have all of my fancy tools, so the presentation will be a bit Spartan, and I will incorporate the R component right into the main lecture. Here we go. Something can have a score on two different variables, x and y. These two scores can be illustrated as a single point. Here we have x equals the number of cats a person has, and y equals the number of mice in their house. Each dot would represent a house for which we have two pieces of information. Here's a house with 2 cats and 2 mice. Here are some other houses. Looking at the extreme values, the house with 4 cats has no mice, and the house with 7 mice has no cats. If we want to predict number of mice, y, we could just always guess the mean of y. This is called the mean model, and it is better than no model at all, or random guesses. But maybe knowing the number of cats, x, helps us guess the number of mice more accurately. Right now, the mean of y is the only bit of information being put to use. Will incorporating knowledge of x, cats, into our model improve prediction? Let's look at a few cases. Here are 2 situations where knowing the number of cats x does not help us guess the number of mice. In this first case, we are already predicting the number of mice perfectly, because there are always 3 mice. In this second case, we are pretty much doing equally bad at predicting number of mice at every value of x, every number of cats. It doesn't improve the accuracy of our predictions. This is yet another situation where knowing the number of cats does not help us guess the number of mice, in part because there appear to always be 2 cats in a given house. We need variation on both variables in order to find any useful patterns or signals. The mean model is better than nothing because it reduces the sum of squared error along the y dimension. That is, if you could only draw a flat, non-sloping line, the mean is the line that has the least distance between itself and all of the points. In the world outside the graph, if you want to guess just one value every time, the mean makes you least wrong in the long run. So predicting that a given house will have the mean number of mice in it is better than guessing randomly, but has plenty of error associated with it. We measure this error by taking each observed value y and subtracting our predicted value from it. We had a house with 2 cats and 2 mice. The mean predicts 3 mice in every house, so it is off by 1 in this case. The more extreme values are off by much more. The house with 0 cats had 7 mice, but since the mean predicts 3 mice, it's off by 4, which adds 16 to the sum of squared error. The house with 4 cats has 0 mice, but the mean predicts 3, so it's off by 3, adding 9 to the sum of squared error. Sum of squared error is how wrong the model is likely to be. Assuming the model generalizes, it is in fact how wrong the model is when used to predict its own values, the values that made the model. Time to apply the concept. Which has a sum of squared error of 0? Only one of these does. The center plot has no misses. The model is perfect. Guessing the mean is correct every time. All houses have 3 mice. The other plots show quite a bit of error. They are terrible models, and their sum of squared error will reflect this. How can we improve on the mean of y? If we had only 2 observations, then we could cut our sum of squared error down to 0 by adding some slope to the line. In this case, a negative slope. From this line, we could predict an unknown y from a known x. For example, someone has 2 cats. How many mice would we estimate? The process of drawing a prediction line gets more complex with more observations. Some of you may recall from grade 9 math looking at a scatter plot and eyeballing the line of best fit and drawing it with a ruler. The idea was to draw the ideal line, the one that gets closest to all of the observations. This was approximating a regression line. That ideal line had 2 elements that we wanted to fix or determine called parameters. The y-intercept and the slope are these parameters. It also had 2 unknowns, things that we were to let vary, so we could plug in a given value of one, usually x, to get the value of the other, usually y. While our grade 9 math lessons likely stated the equation of the line as y equals mx plus b, using m to represent the slope parameter and b to represent the y-intercept, grown-up stats uses a to represent the y-intercept, or beta sub naught, and b to represent the slope. So the equation is y equals a plus bx. If you recall regression equations, the slope parameters are represented as b's. B sub 1, B sub 2, B sub 3. These are coefficients determining each independent variable's contribution to the slope of the line. This is the equation to predict an unknown y from a given x. So our question becomes how, aside from just guessing like we did in grade 9, how do we get estimates for the parameters a, the y-intercept, and b, the slope of our ideal line? We've called this line the regression line and the ideal line. We can also, with even more technical precision and pedantry, call this the least square. To compute it from our data, we, or our computer, use these equations. Errors line, the one with the smallest sum of squared error, or SSE. We start with parameter b, the slope. N in our cats and mice example is the number of houses in our sample, number of dots. Sigma xy is the sum of the products of x and y, so we, or the computer program, multiply together the x and y value for each dot, each house, how many cats for a given house times how many mice for that given house, and then sum the value of these products for all houses. Sigma x is just the sum of the x values, all the observations of how many cats were in each house added together for the total number of cats in all the houses. Sigma y is the sum of the y values, all the observations of how many mice were in each house added together, the total number of mice in all the houses. Sigma x squared is the sum of the square of each observation, x. If a house had 4 cats, square that, so 16. If 3, square that, so 9. And do this for all the houses and then add up all the squared values. We are taking all of our values. We are observing how many instances or houses we have, here n equals 11, and computing the values of the right side of the slope equation. Let's start with the simpler aspects. The sum of the x column, the number of cats observed, is 19. The sum of the y column, the total number of mice observed, is 35. The sum of the products of the cats and mice requires computing a new column. We can then sum down that column. Here is our products column, and its sum, the sum of the products, is 36. One more value to compute to finish this right side of the slope equation, the sum of the squared x values. Our new column is each x squared. In this column's sum, the sum of the squares is 49. Now we have values for all of the unknowns, and we can compute a result for the right side of the slope equation, giving us b, our slope parameter value. We plug them in, and following the order of operations, we get negative 1.51 for our b parameter. We now have the slope parameter, but this is not enough to compute y from x. We need the y-intercept. Well, actually, we don't need the y-intercept to get the y values from the x values. We could just use this formula here in blue. Y equals the mean of y plus b times x minus the mean of x whenever we wanted to get any y from an x. But that, while succinct and elegant, is less intuitive than computing the classic line equation from grade 9, so let's do that. Let's get the y-intercept, then we can predict y from any x. Our formula / trick to get the y-intercept after getting our slope is y-intercept, or a, equals the mean of our observed y minus our computed slope times the mean of our observed x. Keen observers may realize that this is just y where x equals 0, which is what the y-intercept is in our secret blue equation. So we're just using one special instance of that blue equation. So we have two unknowns to compute the right side of the y-intercept equation, the mean of our y values and the mean of our x values. The mean of our y values, their sum divided by the number of observations, is 3.18. The mean of our x values is 1.73. Now we can plug these values into the right side of our y-intercept equation, and we finally have the value where x equals 0, the place at which the least squares line intercepts the y-axis, the value of our parameter, a, 5.79. Our y equals a plus b times x now has both parameters, a and b, computed, so we can input any x to get its respective y value. We can observe or imagine a given number of cats in a house and predict how many mice there are in that house. More to our initial purpose, we can plug in any other x value, as y equals 5.79 was the result of our plugging in an x value of 0. So we have 1 point on our regression line, the point x equals 0, y equals 5.79. To draw our ideal line by hand, we would plug in any other point, any other x. Let's use x equals 3, since it is a value that will yield a result that makes sense, because cat values over 4 would yield negative mice, and mice values over 5.79 would yield negative cats, so let's stay within those bounds. Where we have 3 cats in a house, we predict from our regression line, ideal line, line of least squares, line of best fit, a y of 1.26 mice. This is where grade 9 us would align our ruler to these points and draw the actual line of best fit. The equation describes the ideal line and allows us to predict one value from another. Not perfectly, but a best guess. In the same way that the mean of y was the best guess in one dimension, the y dimension, the regression line value is our best guess in 2 dimensions, the x and y dimensions. So, if we have samples of something, for example homes, and at least interval level data on 2 variables, for example the number of mice in the home and the number of cats in it, then we can use these 3 formulae to predict values of one variable from values of the other. Predicting mice, y, from cats, x, say we have a house with 1 cat, we would predict 4 mice living in the house. Predicting cats from mice, y, with a bit of grade 5 algebra, say we have a house with 1 mouse, we could predict, after a bit of grade school rearranging of the formula, 3 cats living in this house. Note that if number of cats in the house and number of mice in the house were not related, as would be the case with this data, the slope would be a lot closer to 0. What we just did was compute a regression line, or line of best fit, but we also did 90% of the work toward computing a correlation coefficient relating x to y, cats to mice. A 0 slope means x is 0 help in predicting y. Measuring association like this is the general idea behind Pearson's correlation coefficient, r. More sloping tends to mean more relation, or change of y across x, but one challenge is that changing the scale, for example narrowing x by changing inches to feet, could make the slope number larger without changing the magnitude of the actual relation, so we want something standardized, something that tells us the magnitude of relation irrespective of scale, which is why r, the correlation coefficient value, is bounded to only have values from -1 to 1. -1 being a perfect negative correlation. As one value increases, the other decreases perfectly by some specified amount. +1 being a perfect positive correlation. As one value increases, the other increases perfectly by some amount. Note that this also means that as one value decreases, the other decreases. Positive correlation means they move together in the same direction. Here is Pearson's R formula for computing the correlation coefficient, or at least one expression of it. Note how similar it looks to our slope equation. What Pearson added was standardization of scale. Regardless of the units of x or y, which is now represented in the denominator, we can get a meaningful representation of the magnitude of relation, positive or negative, between the variables x and y. The metaphor I prefer for correlation is that of a dance between 2 people. If you cannot predict or anticipate what one dancer will do from what the other does, this is a 0 correlation, and it isn't much of a dance. If one dancer always moves in the opposite manner of the other, this is a negative correlation. If both dancers always move together, whether up or down, this is a positive correlation. Whether you are predicting that dancer B will do the opposite, negative, or the same, positive, as dancer A, if dancer B can be predicted perfectly from A, then it's a perfect correlation. Let's apply Pearson's R to our example. We have most of what we need. We just need the sum of squared y values. All of the other elements have been computed. So, we make a new column of squares and sum that column. Our sum of squared y's is 171. Now we have all we need. Plugging in and following the order of operations, we have a strong negative correlation. Just in case, let's check our work in Excel. Looks good. And remind ourselves of the approved verbal descriptors for correlation values. Note that these are threshold values, so nothing under 0.1 is a correlation, anything 0.1 and over but under 0.3 is a weak correlation, anything 0.3 and over but under 0.5 is a moderate correlation, and anything 0.5 and over is a strong correlation. It's also permitted to call anything 0.7 and over a very strong correlation. Also note that the same goes for negative correlations. In addition to our verbal descriptor, we can also say what percentage of variation in one variable is statistically accounted for by variation in the other variable. This is R squared. R squared is the variation in one variable explained by, or accounted for, or predictable from the variation in the other variable. So we could say that 62.4% of the variation of mice in houses is accounted for by the variation of cats in houses. R squared equals 0.624. We can also say that 62.4% of the variation of cats in houses is accounted for by the variation of mice in houses. This is just as statistically accurate. Recall that statistics themselves tell us nothing of the actual story, causes, directions, or reasons for the relations observed. These things are revealed by how the world from which we got our data was arranged. The more we add data or information informing us of this arrangement of the world from which we got our data, the more we can make causal, directional, or narrative inferences. So here is our report so far. According to these results, 62.4% of the variation of mice in houses is accounted for by the variation of cats in houses. R squared equals 0.624. This represents a strong negative correlation. R equals negative 0.79. But we do not necessarily have what we might call permission to interpret this R and its R squared. After all, the results could be expectable in the world of no relation. We have a small sample of just 11 houses. Based on what we know about samples of this size, how often can we expect results like this when there is no relation? Should we be surprised by this? A significance test will tell us whether we're justified in rejecting the idea that number of cats and number of mice are unrelated. We can perform such a test the old-fashioned way, looking up our critical value based on our degrees of freedom in a table. Our sample size of 11 gives us 9 degrees of freedom, taking p less than 0.01 as our very conservative cutoff. That is, we require our data to be less than 1% likely in the world where x and y are not related before we reject the null that they are not related. To meet this threshold, we need an observed R value of 0.735 or greater. Is the absolute value of our observed R statistic greater than our critical value? Yes! 0.787 is greater than 0.735. So we can add p less than 0.01 to our description, because our observed correlation coefficient is larger than our critical correlation coefficient. It falls in the critical rejection region. We don't have to do things this old school way though. So long as the power is on, we can boot up R. Here I made 2 columns. I concatenated the values together into 2 column vector objects, x and y, and ran a correlation. This gives us far more information, such as a confidence interval for our Pearson's R. It tells us that 95% of the samples of this size should yield estimates of R between negative 0.942 and negative 0.354. It computes a precise p-value, p equals 0.004, and it gives us the t statistic that lies behind this p-value, which we'll get more into in future lectures. In the blinding majesty of glorious technology is where I should probably remind us that correlation is not causation. Two things may be correlated because of a causal relation, but there's nothing in the correlation itself that implies such a connection. Even our 95% confidence interval, which can appear to give us the eyes of God, does not know whether we happen to have a weird or unlikely sample, or how the world from which our data was taken was arranged. Correlations also only look at linear relations. The equation draws the best straight line it can to reduce the sum of squared error. It would draw a straight line right through this relation, which is perfectly predictable using a nonlinear equation, and tell us that there is no relation here. What we have been doing is simple regression, single predictor, linear regression. We have what we need to fill in a simple regression equation. The notation changes a bit, and we read this as y sub I equals beta sub naught plus beta sub 1 times x sub I, meaning our estimated y for a given case equals the y-intercept plus the slope times the value of x for that case. We obtained these values, so our equation is y sub I equals 5.79 plus negative 1.51 times x. If this is our regression equation, we should be able to check these values from a regression function in R. So let's check our line equation parameters in R. I created an object, called it mice, that is the linear model predicting the y object from the x object, and then I asked R to show me that object. The estimated y-intercept, well within rounding error, is 5.79, and the estimated slope, also well within rounding error, is negative 1.51. The r squared has a bit more rounding error, you saw that I rounded up, but still rounds to the same hundredths value of 0.62, and our p-value is the same as well. Of interest might be the significance tests done by R. The significance test on the y-intercept value compares estimation with a y-intercept of 0, the origin, to having a non-zero y-intercept. The significance test on the slope tells us that a non-zero slope predicts better than a slope of 0. In other words, adding the x information to the equation improves our representation of the data by reducing the sum of squared error. How well does the relation between cats and mice let us predict the number of mice in houses? Knowing the number of cats lets us explain or predict 62% of the variation in mice. The relation is very informative. Here is an example from one of the data sets I got to play with during my graduate studies. Our predictor or criterion variable is the age of a murder victim, and our outcome or dependent variable is the age of the person found guilty of the murder. If we took only the mean of our y, offender age, and used it to predict all of the offenders' ages, the sum of squared error would be pretty large. Yet, the regression line, stuck in here ahead of our analysis, does not look like it's doing a dramatically better job. For comparison, I computed the sum of squared error for the mean model. There is a SSE function and a deviance function. Either of them will do this if you don't want to do it the long way. All of the squared errors sum to 4,149. We'll come back to that value later and assess the model quality by comparing this SSE to the SSE for the regression line. But SSE, or sum of squared error, is always computed just by subtracting the actual value from the predicted value and then summing these values. First, let's check modeling assumptions, or make a show of doing our best to assure with statistics that these assumptions were met. What do we have? Independence of errors, constant error variance across your independent variable values, and normally distributed errors. Let's do our best to make statistics that assure our readers that we meet these assumptions. Independence of errors could be found to be violated if the cases were related. So if multiple victims were tied to the same offender who may have a specific victim age preference, and this offender is getting older but his victims are staying the same age. So if all these 19-year-old victims here, surrounded in red, were selected by the same offender as he aged, then this invariance in his preference is relevant for us, but him having multiple data points would be biasing our model toward him. So we check our design and we look for any systematic error in the plots of the residuals, and maybe we test for autocorrelation, because if serial cases were used by accident and they were input sequentially, for example, offender number 1 was cases 1, 2, 3, 4, and offender number 2 was 5, 6, 7, 8, 9, etc., and offenders tended to contribute, as I mentioned, to just one type of residual, whether positive or negative, then a Durbin-Watson test like this one would catch this error with a significant p-value. That said, it looks okay, but hopefully we're not relying only on tests like this to make sure we have independent observations. Hopefully we're more familiar with our data and what we did than that. This, to test constant error variance, is a pred-res plot, short for predicted minus residual, and it shows that the scatter of prediction errors for each predicted y is roughly symmetrical about 0. The red line is not unduly or systematically pulled from the dotted 0 line. There's also no obvious or dramatic fanning or funneling. Not bad. What would violations actually look like? Well, fanning might look like this, with the model predicting younger offender ages better and older offender ages worse. Nonlinearity might look like this, with the model predicting low for younger and older offenders, but high for median-aged offenders. Either way, we don't have the same types of errors across values of x, suggesting maybe we need a nonlinear model or there's some other systemic problem. Next, we have the assumption of normally distributed errors. We want the errors to be roughly symmetrical on either side of our regression line. We can eyeball this from the plot that we already have, and it looks okay. The standard approach is to use a quantile-quantile plot and eyeball whether the dots snake off of the normal line. This has never been intuitive to me, since sometimes what looks like terrible deviations from normal turn out to be statistically fine. I prefer to eyeball the original plot and then run a test like the Shapiro-Wilk. Here, p more than 0.05 means approximate normality. So we've gone out of our way to show that assumptions are fine, as best as we can test. We may now, in good conscience, run the simple regression that lies behind the line that I have already put on the plot. Running a simple regression, forgive my cutting off the data in an awkward way here, but I couldn't get all 85 cases to display well. Running the simple regression gets us these results, showing the statistical significance required to have permission to interpret our findings. In other words, if there were no relation between the age of the murder victim and their killer, then these data would be quite unlikely. So we may proceed as though there is a relation and interpret it. This code down here is how to get a simple non-ggplot graph of the results and draw our regression line onto it, as was done to get our original image. Note that our statistical significance does not quite allay our graph-informed fears that the regression does not add much. We have a y-intercept that is better than having the line cross at the origin. The slope is better than a slope of 0. But looking at the graph, these asterisks don't really allay our graph-informed fears that the regression does not add very much. Supporting these fears is the R-squared statistic, which tells us that the age of the victim only explains 7.3% of the variation in the age of the killer. This seems like a useful check on mindless overvaluing of the p-value. The R-squared value compares the sum of squared error of the mean model to the sum of squared error of the regression equation. We can grab that equation from the results table and compute it ourselves. The difference between the purple sum of the squared error for the mean model and the blue sum of squared error for the regression model is only 303.7. There was a lot of error in the mean model, and there's still a lot of error in the regression model. There's just a bit less, 7% less. And this is what R-squared is. The R-squared value is computed by taking this difference and dividing it by the sum of squared error for the mean. When we say this R-squared shows the percent of variation in y explained by x, we mean it is the percentage of squared error left over after prediction with the mean that the regression equation reduces. Nothing, of course, has been explained, And it's not like we're doing 7.3% better for every case. The regression line improves prediction overall, but makes us more wrong for plenty of specific cases. Look at how much worse our prediction got for this case, reminiscent of Raskolnikov in Crime and Punishment. The model reduces the squared error left by the mean model by a certain percentage overall, but our prediction got much worse for this case. Note, of course, that we were wrong by quite a bit for this case with either model. Okay, but this still isn't very useful. I'm interested in profiling how old the offender will be based on the age of their victim. How much improvement can I expect if I use this fancy and time-consuming approach? Well, I can tell you how wrong you are likely to be even if you use this fancy model. You're likely to be off by 7 years. This value is the residual standard error, which is computed by taking the standard deviation of all the prediction differences. In other words, it is within expectations, where within expectations is within 2 standard deviations, to be off in our prediction of offender age by 2 times 6.8, which equals 13.6 years. The bell curve of our error is such that 1 standard deviation in either direction is roughly 7 years. This statistic can seem more useful than it actually is. It uses a model made with certain cases to predict those same cases. At our most charitable, the best we could say is that it is an underestimate of performance, IRL. Some validation options in ascending order of stringency or severity include leave one out prediction, which would involve making the model n equals 85, because we have 85 cases, n equals 85 different times, each time leaving out the observation that we will be predicting. There's split half prediction, which is randomly selecting half of our data, making the model on it, and then predicting the values of the other half from it and seeing how well it does. And true out-of-sample prediction, predicting the ages of offenders of ongoing investigations using this model and seeing how well we do. My version of this in my graduate work was to predict the results of one sample from a model created from another sample, from another place. Social science researchers will give you very well-sounding explanations for why such severe validation approaches are silly or inappropriate across different groups, and then promptly forget all that and go back to pretending that their research generalizes or has importance outside of their samples. On that note, see you next time. Stay tuned.